So here are our notes. So this should be pretty quick since we did the activity on Friday and kind of hopefully refreshed your brain. So up until this point, you've only ever measured circles in degrees. Okay, this would be like only measuring in inches or like distance in inches or weight in pounds. There are many ways of measuring angles, and we kind of did that activity that said we were going to use radians. Something I do want you to remember is that all circles are similar. All circles are similar. Okay. So remember how radians were transformed. Remember that one radian is the same thing as the length of a radius. This radius is kind of melded around, right? Do you guys remember doing that activity? I know you do. We used the little piece of wire and the little Smarties, and we ended up with like 6.6 and 2 extra sections of Smarties if you were here on Friday. So below, circle A with radius R1 and circle B with radius R2 gives a similarity transformation that shows the two circles are similar. How do I explain how this works? So here's what I did. So remember, first of all, that transformations are things like translate. Do you guys remember transformations? Translate lets you move it to the right or the left or up and down. Okay. And then you have a rotate, a reflection, but you also have a dilation. And if it's going to be a similarity, you have to dilate it. So we want A to be transformed in such a way that the point here becomes exactly that, and the radius is the same. So the first thing that I said is, well, I'm going to have to move it up and to the right. So that's what I wrote. It doesn't have to be real specific. I'm just writing. So I'm going to translate circle A up and to the right. So that, now remember, once you translate something, it becomes, you call it something prime, right? So that A prime, which is the center of my circle, is mapped on point B. So I just took this circle and I moved it up and over to the right. So this is circle A now, but the center is called A prime. Okay, that's just my sketch. So now we have the same center, but I have to make it bigger, right? I have to dilate it. So remember that we said you have a dilation factor. Do you guys remember learning scale factor? Yes. Okay. So here's what I know about scale factor. Scale is always the image, or you could think of it as a model, image or model over the original. Okay. So the scale factor is my image or my model, which I want to map it. I'm mapping A1 or A prime into something. So that's the R2 over the original, which is R1. Okay. So I'm going to have to multiply. Circle A prime by a scale factor of R2 over R1. And we call that dilating. Well, if I were to take A prime and multiply, we know that the radius of A prime is R1. So A prime has a radius of R1. If I were to take that and multiply it by the ratio of R2 to R1, what happens? Yeah, the R1s cancel out, and this gets stretched out to be this great big circle, and we would call it now A double prime or something. That's just proving that all circles are similar. You're just going to have to trust me. All circles are similar. I promise you. Okay. So notice, since all circles are similar, this is the important part. The ratios of corresponding portions of the circle will stay constant. So in our second example, it says two circles are shown below with the sectors Both of these have the same central angle, 60 degrees. Do you guys see that? Both of these have the same central angle, 60 degrees. One circle has a radius of 5. The other one has a radius of 10. So it asks us to calculate the arc length for both sectors and the ratio of the length to the radius. So let's first of all calculate S. So remember that S equals radius times theta, where S is my arc length. So my arc length on the first circle, well, it has a radius of 5 times a degree of what? 60. Yeah, but it's supposed to be written in radians. Yeah, we're going to have to multiply this by what? Yeah, 5 times 60 times pi over 180. Do you guys remember that? I mean, I'm just kind of doing the math. We have to write the 60 degrees in radians. So this cancels out and this becomes 3. So I have 5 pi over 3. That's the length of my arc, 5 pi over 3 inches. I'm going to do the same thing over here. Just change my color up. So S equals my radius times my degree in radians. So we have 60 times pi over 180. You guys need to just kind of remember pi over 180 gets you from degrees to radians. These cancel out and I end up with pi over 3. So my radius, 8 times pi over 3 equals 8 pi over 3. Okay, inches. So that is the arc length for both of them. Now it asks us to find the ratio of the arc length to the radius. So we're going to put the arc length, S, over R. Well, the arc length, 5 pi over 3, divided by the radius, 5. Well, dividing by 5 is the same thing as doing what? Multiplying by... Dividing by 5 is the same thing as multiplying by 1/5. Yeah. So 5 pi over 3 times 1 over 5. And look what happens. And we end up with pi over 3, which is what 60 equals, right? It's trying to show us that we have this common ratio. Again, we're trying to prove that the radius, regardless of the radius measure, if the angles are congruent, then those arc lengths are going to be similar. So my arc length, 8 pi over 3, divided by my radius of 8, which is the same thing as multiplying by 1/8, and I end up with pi over 3. So you're just trying to show that those ratios, like they said, those ratios are the same. Okay. So just as the two circles, I'm just going to put a little note here that says you have two circles that are similar and their ratios of the arc length to the radius is equal. I just want you to know that. So again, this is the formula that we use to find a radian. And if we want to find the arc length, we just multiply both sides by r. And that's what we did on Friday. That's what our foldable says. So if you guys have your foldable out, this is what we used on Friday, right? Over and over and over again. This is just telling you how to find a radian. And we already did that with our little Smarty parties. So go to page 2. So page 2, it appears that the radian measure of a rotation about a circle depends on the size of the circle, but it really doesn't, remember, because every circle has 6.28 radians, which is equivalent to 2 pi, right? We learned that. So here's what we're doing here. So it says, what arc length is traveled in a full 360-degree rotation? Well, remember that if we take the theta and we take the arc length over the radius and we express our answer in terms of pi, well, that just means I'm going to multiply, right? So S equals 360 degrees is 2 pi times r, which is also the diameter. If it's to a, because this is for a full circle, Okay. So remember that one full rotation is equivalent to 2 pi radians. I'm going to just maybe draw our little activity from Friday. So Friday we started with a circle, right? We put our little Smarties on there, 4, 5, 6, 7. And then we just kept taking those Smarties, if you guys remember, and going around the circle. 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6. And we had this little piece left over that let us put 2 more in there. Do you all remember that? Okay. All right. So we see a full rotation of 360 degrees is equivalent to 2 pi, or about 6 radians. And remember, it's 6.28 when we calculate it. The formula for radians is exceptionally easy to use, although it will likely seem like a very foreign way to measure the size of a rotation. So in the following diagram, the 2 sectors are shown with central angles labeled. So I have theta A and theta B. Which has a greater radian rotation? Which has a greater radian rotation? Well, meaning which has a greater angle measure in radians. So let's think about how we do that. So remember, if the arc length equals theta times r, and we're trying to find theta, we're going to take the arc length, which is what? 15, and divide it by the radius, which is what? 6. Which is, I'm going to leave it as a fraction, 5 halves times pi over 180. So which one has a gradient? We can actually leave it as, we can leave it like that. Yeah, leave it as 2.5 radians, because we're just figuring out the radians, not the degree. Sorry, 2.5 radians. Let's do this one. So S divided by R equals theta. 18 over 8 reduces to 9 over 4. Yeah, I hear you. 2.5. Sorry. 2.25 radians. So even though this circle looks bigger, we're talking about radian rotations, and it's bigger because it has a larger radius, but this one has more radian rotations. So theta A is greater than theta B. Theta A is greater than theta B. Think about a pendulum. So a pendulum whose length is 14, that represents a radius, swings through an angle measure of 0.38 radians. What is the length? So remember that the arc length equals the radius times theta. So 14 times 0.38. That arc length in inches is what? 5.32 inches. And that is our lesson. Okay. So pages 3 and 4 are your practice. I think it's only 5 questions. Yeah, it'll be fast. And then we have the delta math. Pages 3 and 4 and the delta math.